Okay, let's get started. Last lecture. The final accumulative experience for ME547 is this linear quadratic optimal control. In linear quadratic optimal control, the general form is like this. Last time we talked about the special form of this problem. The general form of linear quadratic optimal control is you're giving a plant continuous time state space system, x dot equals ax plus bu, y equals cx, with some initial condition. The general goal of FLQ is to minimize this large cost function. Say you start from some initial time, t0, and your control horizon is from t0 to t final, tf. You want to minimize a terminal cost, which is your state at the terminal time, and then with some positive definite matrix S in the middle. So this is a quadratic function of the state at the final time. S being positive semi-definite means that this is going to be a non-negative cost. The second term is about this transient between your initial time and the final time. Your transient is minimizing your state trajectory evolutions, quadratic term about x, with a positive semi-definite q, and then a cost related to the control efforts, u transpose ru. Q being positive semi-definite, again, make sure this is always a non-negative cost. And then this entire thing is non-negative. R, we choose it to be positive definite so that we should avoid putting R to be positive semi-definite, because in that scenario there can be, in the extreme case, R can take 0 if this is a scalar. And we don't want to not penalize the control effort at all. Often Q is taken the form of C transpose C. C is the matrix in the output equation. So often this transient cost becomes X transpose CX. So this transient becomes just the penalizing the output along this trajectory from T0 to TF. We will use this Q for the majority of the time in this class. The special case that we went through last time is this. A special case of the cost function is you start at time 0 and then you want to control the system over the entire horizon to infinity as long as you are running the experiment. And in that scenario, the terminal cost at infinity time, LQ optimal control is going to make sure the system is stable. So at t infinity, this terminal cost is going to automatically become 0. And this cost function and the solution to this cost function makes sense under two important conditions. Is under the condition that the system has to be controllable, or the pair, we usually write A, B, this matrix pair gives a controllable system, and then AC gives an observable system matrix construction. That's the conditions here. Then you can minimize this infinite integration to a single value. That's determined by the initial condition and then a matrix P. And then this matrix P, we'll talk about this in details today. This matrix P comes from a solution technique that is similar to what we used in deriving the Lyapunov equation. The cost is also infinite integration. And this P and Q, they are related by an infinite integral. So P can be expressed as an infinite integration that involves Q. That's how the P here will be related to this. The P here is a solution to this Lyapunov equation. The P here, because we have more terms, our system is also more complex. The P here is a solution to this longer equation so-called algebraic Riccati equation. Under this, the control law that will give you this minimum cost is a simple state feedback control law. We talked about state feedback is very powerful. It can arbitrarily assign the closed loop eigenvalues if the system is controllable. So that's the general form. We will go through, we will see, as it turns out, the general form, this K, the gain for the state feedback is this one. It depends on R, it depends on B matrix, it depends on the P matrix. That's a solution to this algebraic Riccati equation. That is a big overview of the linear quadratic LQ optimal control problem. The solution to this, to derive this, and then to come up with the accurate form of this Riccati equation, actually we'll use something that you all know since perhaps high school. Is this concept of, it's a special optimization. It's about finding the minimum of a quadratic function that looks like this. In the scalar case, this is a parabolic shape. If A is positive, then the shape looks like this. What's going to be the value over here that will give you this minimum value is U equal to negative B over 2A. So that's from high school. What we will use, let's go one step a little bit beyond from here to here, is let's add a little bit more terms that relates to what appears in our LQ problem. If we have R is, in the scalar case, R is a scalar, U is a scalar, all these are scalar. If these are all scalars and R is positive, then the minimum value that achieves, the value for U that achieves the minimum is also this. So it's negative this value over 2 times the coefficient for the U squared term. So it equals negative R UBP. So how did this come from? Let's take a quick review. Why is the value U being this will give us the minimum? Anyone remembers? This is the least square problem. The way that we can write this is, we can say this is, we can complete the squares. That's the technique that we will use today. So we break the first part, RU square, as the square of the square root of RU and then the entire thing square. We're going to complete the square. So this is the square of this. And then if I have 2 times this value, then I'm going to complete the square, add and subtract the square of this term. So this is just rewriting this equation over here. And if I do that, this second least square problem becomes, so equation 2 is going to become R1 over 2U plus. So just rewriting things a little bit. Then we see the minimum is achieved when U is chosen such that the first square term goes away, becomes 0. So if you choose U to be this, then there will be an X over here. Yeah. That's typo. So it's the negative of the coefficients of U for the second term. So it's negative 2 BPX over 2 times the coefficient for the square term. So that's a small typo over there. So we can write it this way, and then you can see if U equals to this term, then the first square term is going to go away. And then you're left with this negative. That's the minimum cost. That is completing the squares to solve this parabolic shape least square problem. And what you're going to see is today we're basically doing the problem, solving the problem in matrix form. All these become matrices, and then the completing the square will appear in a matrix form. That's the process that we're gonna use, the main tool we're gonna use today. So let's take a look at our cost function. Let's take a look at how to minimize this, a big quadratic function in terms of the state and the control input. We will use a similar technique. Let's try to complete the square in a way. Let's try to define some similar quadratic function that appeared in the Lyapunov equation. And then let's take a look at the derivative of this, which equals half of x dot transpose px plus half of x px dot, and it equals half of this, and then we can combine terms a little bit to get half of x transpose a transpose px. The first two terms multiplying outside to times px gives you this, and then for the remaining we have all right, so I take out the 1/2 to the outside, and the inside becomes this. We can see this one has some usual terms, quadratic terms about x, and then some cross product terms between u and x. And in fact, these two cross product terms, you can see they are actually the same. You can see this one, PBU, you take the transpose of this entire thing, it becomes U transpose B transpose PX. P is assumed to be positive, P is assumed to be symmetric, and we will find a positive definite solution in the end. So these two cross product terms, they are actually the same. They hold the same value. What we're going to do is to add and subtract terms to here and create some new quadratic terms about x, and then use the technique in these squares to complete the squares. So the way we're going to do is we're going to do j plus something on the left-hand side, and then it will equal something on the right-hand side. So I'm going to add something on the left-hand side and add the same thing on the right-hand side. All right? I'm going to do add VTF minus VT0. That's on the left-hand side. And on the right-hand side, I am going to, let's define this as the equation star, the cost function. I'm going to add and subtract the same thing. Integration of V dot from T0 to TF is the same as VTF minus VT0. I'm just writing the same thing using different forms. But writing it this way makes me be able to manipulate this large integral a little bit. So you can imagine adding this integral into here, we can bring all these terms to the inside and then have quadratic functions, quadratic terms about x, cross product terms between x and u, and then some quadratic terms about u. let's write this out. You will see more details. We have this, the terminal cost doesn't change. And then inside this integral we have, I'm going to add things to different places now. X transpose QX, add to this one. And then I'm going to shift this term to here. X transpose PAX. And then this cross product term between U and X, there are two of them, hold the same value. And then finally, the quadratic term about U again. So that's on the right hand side, how things going to become. Now, look at here. I can combine this. This is a big quadratic term about X. And then I have a quadratic term about U. That can be regarded as, so I want to emphasize that it can be regarded as a square term of R square root times U, writing it in this form. So what's next? The next thing is exactly this. I have a square term about U. I have a cross product term between U and X. So I'm going to complete the square and create, so using these two, I'm going to add and subtract terms to complete the square so that I am going to have a square term that looks like this. All right, the square term is about U and X. It's about U and X. And then there can be some minus some other terms that is to be determined. Let's take a look at what we can do. This is a matrix form of a quadratic function. What should we add and subtract to create a square term that looks like this? This is the most elegant step in the entire process. After this step, everything becomes clear. So let's take a look at this one. Complete the squares. I already have this broken down. Then I have this cross product term. I am going to write this one such that I will have this term appear first of all, right? This is the step that we used in completing the squares. I'm going to write it at 2 U, so this is a transpose term, so I'm going to try to create this one in here in the middle. So 2 U transpose R 1/2. So I added 1 R square root of R. I need to do a R negative 1/2 to make it balanced. And then I will have B transpose PX. That is just changing the terms a little bit so that I will have a completing the square to be more easy then. And then let's add, so I have intuitively, you can think of this as a number squared, A squared plus 2 times A times B. So I'm going to combine now. This becomes a quantity by itself. So I'm going to say R 1/2 U plus R negative 1/2 B transpose Px. So this is sort of my A, this is sort of my B. I'm going to create a square term about A plus B squared. In the matrix form, it should be the transpose of this times itself. Let's call this term 3. So that's the target that I'm going to create. And then I might need to add and subtract certain terms. So plus something to be determined. Let's evaluate this. Then things going to become clearer. This one is going to be R 1/2 U transpose times R 1/2 U. So it's U transpose R 1/2 U. R is symmetric. It's positive definite. So its transpose equals itself. We can just write R 1/2 in here. That's the first term times this. And then the second term will be the transpose of this one. X transpose P transpose. P is positive definite, or it's symmetric to begin with. So P transpose equals P. And then B R 1/2. So the transpose of this one times the first term in here. So it's R 1/2 U plus there are a total of 4 terms. We finished this term multiplied with the first term and this term multiplied with the first term. Now is this term multiplied with the second term in this parenthesis. It's going to be U transpose R 1/2. Second term is this one, R negative 1/2 B transpose Px. And then finally is this term transpose times the second term in here, which is going to be X transpose P B R negative 1/2 times R negative 1/2 B transpose Px. So that's the quadratic term here, expanded out. It looks long, but actually there are many things that will cancel out. This R 1/2, 1/2 kind of things, they're going to combine into just R. This becomes R. And then you have R 1/2, R negative 1/2. This term is going to cancel out. Then here, this is going to become R inverse. So that's the square that we just completed. Now, to make this entire thing to equal to this, what should we add or subtract? So we compare this and just see what is the difference between these two. We have U transpose RU, so we have the first term is the same. This cross product term, we have U transpose and then R 1/2, R negative 1/2 times B transpose Px. So we have one of them appearing here. This one is actually the other half because this one is the entirely transpose of this cross product term. And they are the same. So this 2 times this whole thing together is exactly these two. To make them equal, we just need to subtract this final term from here. But after we do this, we have successfully, what we have essentially done is to have replaced this one now with, we have actually found out all the 2 terms that we wanted to write down at an earlier time. So we have the minus sign to be determined is this, X transpose PB R inverse B transpose Px. And then the square term that we completed is r 1/2 u plus r negative 1/2 B transpose px. Once you do this, the problem is essentially solved. We will have the Riccati equation that's going to appear. We will also have the optimal control law. All right, so to see this last step, you can recognize we have a big quadratic term, two big quadratic terms actually. This is a big quadratic term about x. This is another big quadratic term about x. And then this itself is a second non-negative term. Remember, our goal is to find a control law. We have to find the control algorithm that minimizes this entire thing. In here, there's no control term. U doesn't appear in here. U doesn't appear in here either. So you can't change these two terms. The term that you can influence is this term, this non-negative term. So what is the best way that you can do is to make this to be 0. So the best thing that you can do is to make this 0. So the optimal control law, therefore, U optimal, UOPT, is negative R 1/2, R negative 1/2. So it's negative of R negative 1/2 times this term, R negative 1/2 B transpose PX. If U equals this, then you can see, plug it inside. This R negative 1/2 cancels with this R 1/2, and then the remaining term is going to exactly cancel out the square term. In other words, it's negative R inverse B transpose PX. And you can see the beauty here. This is exactly a state feedback law. It's a static gain. This gain has a very special structure, but it's a static state feedback law. And this is the formula that we introduced at the beginning of today's lecture. Cool. So we have now the optimal control law. Let's take a look at the remaining piece about this big quadratic term about x. You can combine these two together and get, I'm gonna sacrifice the space here. So 4 plus 5 gives you this big quadratic term x transpose A transpose P plus PA plus Q minus this big matrix PBR inverse. That is the big quadratic term about x. So what is the best possible scenario for this quadratic term? Is when this entire thing in the middle is 0, right? If this entire thing in the middle is 0, then this whole transient cost function becomes 0. So the best you can do is to make this 0. And then when this becomes 0, that is actually the Riccati equation that you saw earlier. If you don't have this, making this 0, that's the Lyapunov equation. And for the LQ optimal control, it's slightly more involved. It has this extra term, and it's called Riccati equation. So now this is the full result of LQ optimal control. You now know what's the optimal control law and then the equation that must be satisfied. In practice, you can see the two actually play good synergy together. In your optimal control law, you need R, which is given to you. You need B is also known. You need P. So you need to be able to have the value of P to implement the control law. And where do you get the value of P? Is from here. Because A is known, Q is given, and then B is known, R is known. So P can be solved from this Riccati equation. That's about practical implementation. Okay, this is the core of LQ solutions. There's one tiny small piece that I will add now to complete the picture. The tiny piece is this. Here, when the horizon is infinite, we can take P to be a constant. Actually, we can take P to be dependent upon time too. When the horizon is finite, this V, function of time, X is a function of time, P can also be a function of time in this most general LQ solution. So in that case, when we take V dot, we have to take the chain rule. We have to take the derivative of the first term, take the derivative of the last term. The most generic LQ solution also has the derivative of P that appears in here. That actually just changed things by a tiny bit, not too much. So you have this extra term, you have extra term here. Extra term here, and then it's going to appear also in here as one extra term. And then it appears, so it's a quadratic term about x, it appears also in here. Then the other terms doesn't change very much. So this one, in the infinite cost, it appears one extra term that's going to be combined into this Lyapunov-like equation. And it's going to appear, this doesn't change, this doesn't change, so it appears as one extra term in here. The rest of the derivation is the same. So it's just one extra term in the Riccati equation. Okay, so I've introduced all the core steps. Let's review the results on the screen a little bit. We are considering the performance index. This is so-called the finite horizon LQ. The optimal control feedback law and the Riccati equation, they can be solved by numerical tools, both in Python and the MATLAB. This Riccati equation here, this is the ordinary differential equation, you can see, about P. And then we have the boundary conditions. We know the boundary value of this P matrix at TF. So we can do numerical integrations and obtain P from there.